Okay, again, this is for the video. If you ever want to watch it, you can watch it. You don't really need to, but for people who aren't here, I'm going to post it on the class page. Remember yesterday, yesterday we were talking about something called reaction quotient, Q, and I gave you that sheet to work through. Were you okay with all that stuff? Okay. Just remember, if we're talking about a reaction, we can solve for what's called the reaction quotient, set up exactly the same way. If I have, A moles of it, or A plus B in equilibrium with C plus D, whatever, well, we would just set it up the same exact way. Concentration of A raised to the A, concentration of B raised to the B. Again, this looks exactly like the same expression for Kc. You'd write it the same exact way, but you put in concentrations that are given. And if Q happens to equal K, you're at equilibrium. If Q is greater than K, well, you're not at equilibrium. Likewise, if Q is less than K, you're not at equilibrium. If Q is greater than K, it means you form too much product, so you're going to have to come back in this direction. And if Q is less than K, it means you're going to form more products. That's all those. Reaction quotient should be pretty simple, pretty straightforward. So let's move on to today's topic. Today's topic is called LeChatlier's principle. Now, LeChatlier's principle says if I have a system at equilibrium, if you put a stress on a system at equilibrium, the equilibrium, I'm just going to call it the EQ, will shift to minimize the stress. You might be thinking, what does this mean? You're talking about putting a stress on a system. Well, if I have a system at equilibrium, think of it this way. I have a well-established ratio of products to reactants. And if we just take a look here, let's say I have my hypothetical reaction. And at equilibrium, I know I have a certain concentration of products, certain concentration of reactants, and that establishes the equilibrium. The fact that we have a reaction at equilibrium. Now, when I say put a stress on a system, what can I do? I can change concentrations. That's one way. Change concentration. So let's say, for example, I add more A to my system. I have this beaker right here, and well, this is not a beaker, but let's pretend I have a beaker here, and my system's at equilibrium, and I decide to put some more of chemical A in there. What do you think is going to happen? I put more A in there, it's going to push to get rid of that A. Right? It's gonna move in the direction of forming more products. Yeah. What happens if I put more D in my cup? Right? It's gonna move toward the reactants. That's LeChatlier's principle. It's so easy. You apply a stress to a system in equilibrium, and the equilibrium shifts to reestablish equilibrium. So you can change concentrations. What happens if I could magically, let's say I have this reaction, and maybe this is a gas, this one here. Maybe it's a gas, and these could be aqueous or whatever. And all of a sudden, I'm able to come in and just suck out that gas, just remove that gas. What do you think is going to happen?
It's going to try to fill in that empty space.
It's going to try to shift. Good morning.
Morning, Doc.
Morning.
Sorry, everybody. Have a nice day.
Thank you. It's going to try to shift this way in order to make more D. That's LeChatlier's principle. Now there's another thing that we can do, and I'll erase this and write it up here. Matter of fact, let me do that now. Okay, so 1, we can change concentrations. Number 2, we can change pressures. Okay, let's take a look at this one. Yesterday I had mentioned that we can, if we have a reaction that's all gas, like our old favorite one here, N2 plus 3H2 to give NH3, 2 of those. Well, these are all gases. And we could write an expression in equilibrium, K sub P, based upon pressures. That would be the pressure of ammonia squared divided by the pressure of nitrogen times the pressure of hydrogen cubed. So if I have the right pressures, I'll be at equilibrium. Now, let's say I have a container, a rigid container, and I've got my gases in here. If I increase the pressure, you got to think a little bit. If I increase the pressure on the whole system, this is going to want to shift in a way as to alleviate that stress put on the system. And this is where you have to pay attention, because if you look on this side, I've got 1 and 3. I've got 4 moles of gas on this side of the arrow, 1 mole of nitrogen, 3 moles of hydrogen. And on this side, I only have 2 moles of gas. So if I increase the pressure, if I decrease the volume or increase the pressure, it's going to want to shift toward the side with fewer moles of gas, because the pressure has more of an effect on the 4 moles of gas. Likewise, if I decrease the pressure, it's going to shift toward the side with more moles of gas, because it wants to maintain those ratios of pressure. Nothing to it. LeChatlier's principle. One more thing we can do. Change temperature. Some reactions are exothermic. In other words, they give off heat. So, just trying to think of one off the top of my head. Let's see if I can just even look at the sheet here. Yeah, let's take a look at question 3. I've got some crazy chemical compound here. 2Hg3O in equilibrium with 6 mercury and oxygen. And it says here, delta H is negative 25 kilojoules per mole. Now you look at that, and these are all gases, so we could figure out some things about pressure and concentration and whatnot. Now, that delta H being negative, do you remember what a negative value meant for whenever we had a negative value for heat or for Q or for H, delta H? Not absorb. It's going to give off heat, right? So if you look at it this way, this is giving off heat. So we could say heat is like a product of this reaction plus heat. Okay? If it's positive, that means you need heat on this side because it absorbs heat. Right? Now, if I change temperature, like let's say I have this reaction and then I carry out at room temperature, and then I carry it out by putting it in an ice bath. If I'm putting it in an ice bath, I'm removing heat from the system. So the reaction is going to move toward the side that will give off more heat. If I carry out this reaction and I carry it out in a very hot room or on a burner or something, well, it's like I'm adding more heat. So it's going to shift away from that heat. So if delta H is negative and you decrease temp, it's going to move toward the products. If delta H is positive and you increase temp, it'll move toward the products. That's everything you need to know about LeChatlier's principle. Let's take a look at number 3 since I started doing it here. And they ask you different questions about number 3, this reaction here. They say, what's going to happen if I add more of this mercury oxide? Which way is it going to go? Right? Put more of that in, wants to get rid of it. Yep. How about if you decrease the volume? What happens if you decrease the volume? What happens to the pressure? If you decrease volume goes down, pressure goes up. You've got 7 moles of gas on that side, and Joey has it. Yeah, it's going to shift back that way. And then temperature is increased. I increase temperature. Yeah, back that way. So I'm telling you, I think this is probably one of the easiest concepts to understand. So just take some time now and work on this. And if you have any questions, just ask me.